Good afternoon. Sorry I can't be there with you guys today. It's my turn to stay home with the sick kids. Hopefully, I'll be back tomorrow. So on Friday, we took the test over chapter 1. I have those with me at home. If they're not already in Harmony by now, check by the end of the day and they should be there. And I'll have the paper copies back to you when I return to school. If you were not here Friday and you're here today, please be ready to take the chapter 1 test when I return to school. If you did not get your vocabulary for chapter 1 turned in, or the labs that were due, please make sure that you are getting those completed. So if this doesn't happen to take the entire class period today, please use that time to go over to the lab and finish whatever labs you need to complete. All right, so today we're going to start chapter 2, which gets into what the Earth is made of. So chapter 1 was kind of a preview of the different spheres of Earth and the different areas that fall under the study of Earth and space sciences. And we did a short lab using some of the materials of Earth. And we found the density of those different rocks to try to figure out how the layers on the inside work themselves out the way that they did. And we found out it has something to do with density. But we didn't really look very closely at what those materials were made of. They were kind of a preview of what was to come. So over the weekend, you were supposed to have read chapter 2, lesson 1. And there are 2 different papers you're going to get today. The first one is the study guide. They're on the front table in the front of the classroom. And the other one is notes. And the notes go along with the slides that I'm going to use today in class, as well as the rest of the chapter. And you'll be able to see that once you look at them. So please take a moment and make sure that you have the study guide packet and the notes packet off the front table. Okay, so put your study guide off to the side. You'll do study guide section 1. It should be the front and back of the first page of the packet. If it did not copy front to back, it's the first 2 pages of that packet. It looks a lot like chapter 1, and we'll go over the answers to that tomorrow. For the notes, chapter 2.1 is called Matter, and it relates to our at the bell question. So our at the bell question asks you, what is this? And what do you know about it? Hopefully this is familiar to you, especially if you have taken chemistry or are planning on taking chemistry, currently taking chemistry. We need to do a little bit of a chemistry type review before we can get into what the Earth is made of, as far as samples big enough for us to handle. So please record what you think that is and what you know about it on your at the bell sheet. So the other packet that you have should have 4 slides per page, and you'll know it's the front because you'll see a black and white version of this image of this man or woman, it's hard to tell, standing in a cave of giant crystals of some sort. And hopefully by the end of this chapter we will know where they are. Our samples will not be that big. So to get started, minerals are building blocks of rocks. So we're going to be looking at minerals in chapter 2 and then move on to rocks in chapter 3. So a mineral is natural, inorganic, a solid, possesses an orderly internal structure of atoms, and have a definite chemical composition. A rock is any naturally occurring solid mass of mineral or mineral-like matter. So you need minerals to make rocks. So here's an example. Aggregates are made from different materials joined together. So granite, maybe you have granite countertops in your house, or maybe you enjoy watching HGTV where they're always putting in granite countertops in people's houses. Or maybe you have a sample of this yourself. I know there are several people who are into collecting crystals and rocks, so you might have granite as part of your own collection. So when you look at granite, the rock, you can see that it appears to be made of more than one thing. There's a definite mixture of materials there, and that's what they mean by aggregate. It's a combination of more than one thing. And you can see at the bottom, they identify the different minerals that make up granite rock. Quartz, hornblende, and feldspar. And you can see that they themselves have different features about them. One's kind of shiny, sparkly. This one's kind of a shiny black. This one's more of a matte, kind of a pink color. And you can see those individual pieces in this particular type of rock. So that's what we're going to be looking at, minerals, before we move on to rocks. So on your version of the slideshow, there are some blanks. The answers that you need to fill in for those blanks are on the screen. If you miss any of these, you can ask somebody, or you can go to the link to the slides themselves, which are on the weekly planner, or you can rewatch this video. So elements are the basing building blocks of minerals. So that's why we have to start with a matter review. We need to look at what the elements are that make up the minerals, that make up the rocks. There are over 100 known elements. They're defined by their number of protons. They are grouped if they have the same type of atoms. And it's a substance that can't be broken down into simpler substances by chemical or physical means. So atoms are the smallest particles of matter, and the smallest part of an element is an atom. Atoms, though, themselves are made of even smaller pieces, the largest of which are called protons, neutrons, and electrons. And this is important for how the crystals and the minerals form. So atomic number is the number of protons in an atom's nucleus. I show you here what the nucleus looks like. Here in the center. You will find both the protons and neutrons in the nucleus. But the atomic number generally reflects the number of protons. There's also a third part, little particle in an atom called the electron. And there's a couple different versions of what they think atoms look like. This one shows them having like little orbit paths, which is helpful to think of it that way. There's also kind of a shell version where if you imagine kind of like the spheres of Earth, they kind of encompass all the way around. The little electron could be anywhere on that level of shell. Some of them use the electron cloud model. The cloud kind of gives it more of a less organized kind of image, like it could go anywhere on the outside, but really they have levels, so more like clouds in the shape of a shell, or a very open orbit. Like it's going to be the same distance away at any given time, but it could be anywhere. Like it's not going to just stay going this way. The periodic table of elements, that was the at the bell image. This is where we have organized all of the different elements by their atomic number, which tells you how much of the protons and neutrons and electrons they contain. And they are organized by their properties. So there's some tendencies with their electrons, and then there's also a tendency to lose electrons here in the middle. And then you can see there's a large section of elements that are considered a type of metal, kind of an in-between metal, and then a non-metal. And that will be important also when we look at how these different atoms combine to make the molecules that make up the minerals that make up the rocks. There are some variations within the elements. Ions are positively or negatively charged atoms due to an electron gain or loss. So when you're dealing with different types of atoms and the different numbers of electrons that they have, the way that they're organized in these shells and in these levels, the outermost level isn't always filled to the maximum number of electrons, so it makes that element not as stable. If they're missing an electron in that outer shell, it would really like to get one to just feel more stable. Or if it has an extra one, it wants to get rid of it. So those types of atoms are going to seek out their opposite. If you need an extra electron, they want to find one that has an extra electron, and vice versa. If you have a positive charge, you have given up your extra electron to feel stable. You now have more protons than electrons. If you gain an electron to make your outer shell feel better, feel stable, you're going to have more electrons and protons, and then you would also be considered negative. Isotopes are atoms with the same number of protons but a different number of neutrons. So it's also possible for them not to have an equal amount of protons, neutrons, and electrons. So you're an ion if you have a different number of electrons than your protons. You're an isotope if you have a different number of neutrons compared to your protons. Clear as mud? Yes. All of those words have on in them, it seems like, so it gets a little bit confusing. So you'll want to look at the mass number to see how many protons and neutrons it has, to get an idea of how many electrons it should have. And then there's also something called radioactive decay that they explain in the book. Most of the nuclei, or the proton-neutron part in the center of an atom, is stable. But in some atoms, they decay. They're going to lose those over time and become an isotope. They're going to have a different number of protons compared to their neutrons. And we look at those isotopes compared to like the one that's expected to see how old something is. So if we find a rock that has, let's say, carbon in it, and we know that carbon should have a certain number of protons and a certain number of neutrons, and we find this carbon that has the right number of protons but not as many neutrons, we can look at how many it has and compare that to its known decay rate and be able to tell you how old that rock is. So we use radioactive, they call that radioactive decay. We use radioactive decay to determine the age of fossils, rocks, and minerals. So when you read that, the Earth is this many years old, part of that's going to come from being able to look at radioactive decay. Most people, when they think or hear of radioactive, they think of like uranium, which does decay. But carbon's not going to act the same way as uranium, okay? It just means if they're radioactive, that means that they have a decay tendency within their nucleus. It's not going to necessarily make you glow in the dark and give you cancer, right? Okay. So we talked about how the atoms that have an extra electron or not enough electrons in this outer kind of shell or outer layer of their cloud, are looking for a partner to be stable. The outermost shell is called a valence shell, and the shells themselves want to have 8 electrons in them. So that's the octet rule. The atom will gain or lose or find a way to share electrons in that outermost area of their particular makeup to become stable. Chemical bonds are one of the ways that atoms can achieve a full valence shell. So they either transfer, give or take, or share their electrons in a chemical bond. When the atoms do this, they create something called a compound, where you have 2 or more elements chemically bonded in specific proportions. A synonym that you're probably familiar with for compound is a molecule, like water. What is water made of? H2O. What does that stand for? So hydrogen and oxygen. What's the 2 tell you? It's like the recipe, right? So there's 2 hydrogens, H2, and then an O for oxygen. So it says 2 or more elements, you have hydrogen, you have oxygen, chemically bonded in a specific proportion. You have to have 2 to 1 every time. H2O is water. HHOO, not water. So when an atom's highest energy level does not have the maximum number of electrons, it is likely to form a chemical bond with another atom. So ionic bonds. Atoms that bond together when oppositely charged ions attract. This compound is going to have new properties compared to the elements it contains. It will form a rigid solid with a high melting and boiling point, but it will be a poor conductor of electricity. So if you think back to the periodic table of elements, you'll want to look at groups 1 and 2 and 16 and 17. So groups 1 and 2 says tendency to lose outermost electrons to uncover a full outer shell. And then 16 and 17 are right here. Tendency to gain electrons to make a full outer shell. So chlorine, for example, and sodium. Sodium wants to get rid of some electrons. Chlorine needs to get some extra electrons. That's what we have here. So the transfer of an electron from sodium to chlorine forms Na and Cl ions. The arrangement of NaCl ions create what you know as salt. Chlorine is a very, very volatile element. It was used in the past in warfare when the chlorine would be released in some kind of an explosive device. It would mix with the water in people's eyes and blind them. Sodium, normally by itself, is like metallic silver cream cheese, is what it looks like. And it is also very volatile. So these 2 atoms are not stable. To become stable, they seek out another electron needing or electron that has extra to give away, and they combine to make salt, which is not dangerous, unless you have high blood pressure, right? It's not metallic cream cheese, and it doesn't explode when it hits water. So when you make these atoms stable, they create something new that is more stable in many cases with group 1 and 2 and 16 and 17. But because they become ions, their electrons are not very flexible, so that makes them not a good conductor of electricity. To be a good conductor of electricity, the electrons need to be able to move around within the mass. So good for eating, not good for wiring your house. A covalent bond is where they will just share their electrons. They're not necessarily giving them away and becoming ions that bond together. These create substances that have low melting points and low boiling points. Also, poor conductor of electricity because they're sharing the electrons, which doesn't allow for a lot of flexibility, even if you melt the original substance. Covalent bonds are what hold together many molecules that you are familiar with, as well as common gases. So you breathe oxygen, but it's not just individual oxygen atoms. It's what's called O2. There are two little oxygen atoms that covalently bond together, and that's the molecule that you need to breathe. O3 is ozone, which is in the atmosphere. O4 would be something else. O just by itself is just an oxygen atom. You can't breathe that. You need to have the one that's bonded together. Another one that you're probably familiar with, which we talked about earlier, is water. Water is a covalent bond. So here they talk about the H2 that you breathe. It also shows you quartz, which is silicon dioxide. So it's made of silicon and oxygen. Oxides are made of oxygen. And sometimes when these are put together, the way that they share their electrons, they kind of drift a little bit to one side, making them a little bit, the molecule itself is a little bit positive on one end and a little bit negative on the other. And they call those having poles, a polar bond. Water is like that. One side, and that's also what helps make it look kind of bent in its shape. Hopefully you guys remember that. Looks like Mickey Mouse upside down sometimes. And the oxygen side of the water has a little bit different charge than the hydrogen sides, and that makes them interact with other substances as far as wanting to dissolve or mix or not. Kind of affects how that type of molecule interacts with other molecules. Metallic bonds are packed metal atoms have valence electrons that are free to move throughout the structure. So they're not going to another one. They're not taking one from someone else or giving one up to someone else. They're also not like just sharing between these two. The electrons are able to just flow through and kind of just go in this kind of sea of electrons free to move throughout the structure. And because they have this flexibility, as long as they're somewhere near a proton, they're not going to just shoot off and go by themselves, you can pass electricity through them. If you push an electron into this situation, you're going to be able to get one to go out the other side, and that's what helps the current flow. So metallic bonds make metals, and it makes the metal malleable. That means it's not going to be this rigid, hard, shattering type of material like a cube of salt would be. If you hit it, it's going to break apart into pieces. Malleable means it can bend and be shaped. It also makes metal ductile, which means it can be stretched into wire, which is what we use in our electronics. So they're a very good conductor of electricity because they allow the new electrons to come in, and it just kind of does like this domino effect, and we'll pass them on through. All right, and you can see that that's the end of the notes for section 2.1. So we will end there for today in the packet that you have for fill in the blank. If you missed any of the blanks, please ask a neighbor, or you have access to the slides that I'm using in the weekly planner. This link will take you to the slideshow and you can fill in the blanks on your own. That's useful if you are ever absent and you see that we're taking notes that day. You can at least fill in the blanks, or you can attend the Google Meet that's open and do the work right along with us. If there's any time left in your class period, you can work on the study guide 2.1. If you did not read the section 2.1, please read it. This was a brief version of chemistry. There's a lot more to this discussion of atoms and bonds, but this is just the little bit that you need to go forward with understanding how minerals combine and pull themselves together with the different elements that they consist of. So you can work on the study guide 2.1, reading the section to help you. Also, if you still need to finish a lab and there's time left, now would be a good time to take your lab sheet over to the other room and finish your map labs if that's something that you need to work on. Tomorrow we'll go over study guide 2.1, and if you have any questions, we can go over those then. Have a good afternoon.